Well, hello everyone, and welcome to lecture 12. 12 being the number of completion. This is the final lecture in this course. And today we're going to have a more complete discussion, in fact, of the topic that was brought up at the end of lecture 8 and also touched on at the end of lecture 6, which is the topic of Cauchy and Sinh and what they mean and where they come from. And here we're going to start off on our journey in a different place and end the journey in a different place than we did last time we visited this question. And we're going to use integration by parts in order to be able to accomplish the journey in the fashion that we will be accomplishing it this time. So, back to the hyperbola, the so-called unit hyperbola, x squared minus y squared equals 1. Of course, we're only going to concern ourselves with the left branch for our conversation of Cauchy and Sinh. Of course, this hyperbola also includes a branch over here, which is the mirror image of the one on the right, which we should not be concerned with. And what we are going to concern ourselves with is this area right here. So we have a given value x right there. Can you see that? Yeah, good. So we want to express this area in terms of x, and then eventually we'll want to express x in terms of that area. But today we're going to start with expressing the area in terms of x. So the area of this shaded region is going to be the area of the whole triangle minus the area of this region right here. Okay, so and this point right here, this point is the point x, and the square root of 1 minus x squared, of x squared minus 1. That's what we get from rearranging this hyperbola. We get y equals plus or minus, but we're up here on the plus branch. So plus square root of x squared minus 1. So the height of this triangle is the square root of x squared minus 1, the total straight triangle right here. And the base is x. So the desired area, and let's call this desired area A. The shaded region is A. So A equals x base times x squared minus 1, height over 2, minus the area of this curvilinear triangle right here, right? So in order to get the shaded region, we take the whole triangle and we subtract the non-shaded region. And that is going to be, we're going to express it as an integral. It's integral of x starting at 1. This is 1 right here. Or, sorry, we'll call the variable equation, we'll call u. So u starting from 1 and going to x. U starting from 1 and going to x. And the integrand is the function by which this curve can be expressed, and up in the first quadrant, as I mentioned before, this curve is y equals the square root of x squared minus 1. So it's going to be square root of u squared minus 1 du. So now what we're going to do that's a bit different from what we did last time is we're going to use the same trick that we've used for finding the integral of the natural log and finding the integral of arctangent and other things. And what that is we're going to make a u appear out of nowhere for integration by parts in this integral. So this is, in fact, I'm just going to erase the figure up here. Of course, you can screenshot it or rewind. You probably will want to rewind at some point to look at the figure. I'm going to erase it for now to give myself more room. So this expression equals, carry over to this part, and then subtract, integrating by parts. And what we're going to do is we're going to have as we're going to make a u appear right here, so that's going to become u times square root of u squared minus 1 divided x and 1, and then subtract the integral from 1 to x. Then we're going to have a u, the u that we brought in, then we're going to differentiate this thing right here, and the derivative of the square root of u squared minus 1 is u over the square root of u squared minus 1 du. So in the terminology that I've used elsewhere here, what we're using is u is going to be f, and so capital F in the terminology I've used before, little f equals 1, and little g, in fact the only g, equals square root of u squared minus 1. So then this right here is f times g prime. That's what this integral has become, is f times g prime. Okay, so that's the justification for why for how I've done that. But then the question is, why have I done it? So, keep in mind the quantities that we're integrating are still the area of the shaded region in the original figure. I'm just crossing this stuff out, or erasing this stuff in order to create more room. So yes, why have I done this? I've sort of pulled these things out without saying why I was doing them, but all sorts of magic is going to happen. So here we have this equals x times the square root of square minus 1 over 2, and minus x over the square root of x squared minus 1, evaluated at the top, and then subtract the same expression evaluated at the bottom. But when you put a 1 in here, this becomes square root of 1 squared minus 1, which is just 0, and so it disappears. And so this is the only thing we have from this term. But then this other term becomes, we're going to rewrite it as, and this rewriting is where things become more special. So this, of course, this u can be grouped in as u squared, and then we can rewrite this as u squared minus 1 plus 1 over the square root of u squared minus 1 du, right? We've just added 1 and subtracted 1, but well, why have we done that? We've done that because this term right here can be replaced by canceling one of these square roots, and then we'll just end up with for this integral, we end up with the integral of 1 up to x of the square root of u squared minus 1 plus 1 over the square root of u squared minus 1 du. And this is, of course, this just becomes minus x times the square root of x squared minus 1 over 2, right? Because we have 1/2 of this quantity minus the entirety of this quantity, and this is still minus. And so this is the expression that we get from this step. You may want to take a second to make sure everything tallies here. But now if you remember, this quantity right here this quantity is exactly the negation of A. So recall A equals x times the square root of x squared minus 1, the area of the big straight triangle, minus the square root, minus integral 1 to x of the square root of u squared minus 1, this being the non-shaded curved triangle that needs to be subtracted out of the straight triangle in order to get the shaded curved triangle that we want. But what we have shown through all these manipulations, because we've just been dealing with A this whole time, so what we've shown is that A equals this, which is minus A plus the integral of this. So of course we can split this up into two integrals, right? So this becomes square root of u squared minus 1 u. And this is all within the minus sign, so I'm going to distribute the minus sign over here now. We have another integral, 1 to x. I still have it circled because this quantity right here is A. So we have is that A equals minus A. A equals minus A plus the integral from 1 up to x. This is too close to the last formula. A equals minus A plus the integral from 1 up to x of 1 over the square root of u squared minus 1 u. And in this, from this we can do the same trick that we've done several times before with, well, a few times before when we looked at integration by parts of the trig functions. So we can add A to both sides. So we end up, so A equals this, then we can add A to both sides. So we get 2A equals this, and so then A by both sides by 2, and we get A equals 1/2. The integral from 1 to x of the square root the integral from 1 to x of 1 over the square root of u squared minus 1. Okay, so I'm going to now, recalling what we talked about before, or you could just say I'm just doing it just because, just why not? I'm going to name this quantity right here t, and we'll express it as t of x, a function of x. So now we have that A equals t of x over 2. You can think of it as mirroring what we said. It's, just being the same as what we said before in lecture 8, or you can just think of it as a black box. For whatever reason, I'm going to call this quantity t. For reasons that will become apparent. And you could play this lecture in reverse. So now I'm going to make the assertion, the strange assertion, that t of x equals the natural log of x plus the square root of x squared minus 1. And this is quite a strange assertion indeed, but I'm going to show that it is so, because it is an antiderivative, and it's antiderivative because t prime of x equals, we can apply the chain rule here, right? So we get 1 plus x over the square root of x squared minus 1 all over x plus square root of x squared minus 1. So then if we multiply the numerator by x squared minus 1 over x squared minus 1, be sure to keep this separate from above, and then just multiply the denominator by 1, do nothing to it, then what we end up with is that this 1 over x squared minus 1, and then in the numerator we get square root of x squared minus 1 right here, and then this one will cancel with the numerator here, and we'll get it plus x. Right, and this right here comes from this leftover part, right there. Then it's all over x plus the square root of x squared minus 1. But of course, now numerator and denominator are the same, so it's just 1 over the square root of x squared minus 1, and you can rewind if I erased that too quickly and you didn't get a chance to convince yourself of it. But, okay, so it has the right derivative, and so that means that I've asserted that this is true, but what we can really say is that t of x equals this thing evaluated at x minus this thing evaluated at 1, right? Because if we call this, so say for a second we quit asserting that this is what t is, we call it f of x, capital F of x, so this is the derivative of capital F of x. So what we've actually shown here is that t of x, because f is an antiderivative of the integrand, t of x equals capital F of x minus capital F of 1. But capital F of 1 is the natural log of 1 plus 0, which is 0. So this term disappears, and t of x is just equal to f of x. So in fact, we were justified in saying this is t of x. Okay. So that's that, and yeah, so now we have t in terms of x, and I notice I haven't said a word about Cauchy or Sinh, and if you remember in the past when I brought up Cauchy and Sinh, the expressions for them seemed to come somewhat out of nowhere. It was just like, okay, here's the expressions, they happen to satisfy the polynomial, the x squared minus y squared equals 1. But now that we started our journey with area, and now I'm going to propose to finish the journey with the expression for Cauchy and Sinh, as opposed to sort of the opposite last time. So okay, so a equals t over 2. I'm gonna drop the x's now. So we've shown that a equals t over 2, where t equals ln natural log of x plus the square root of x squared minus 1. All this stuff inside of the natural log. So now let's express x in terms of t. So how are we going to express x in terms of t? Well, first we're going to raise e to both sides of the equation. So the e to the t equals, and then e to this thing, the e to and the natural log of will cancel each other out, because that's exactly what the natural log does. So this becomes x plus square root of x squared minus 1. But then this seems like perhaps it might feel like a dead end. How do we proceed from here? But the good news is that that we can take the reciprocal of both sides of this equation. Take the reciprocal of both sides of this equation, and we get 1 over e to the t. 1 over e to the t, which is of course the same as e to the minus t, right? E to the minus t equals 1 over e to the t, which equals 1 over, very pretty line, equals 1 over x plus the square root of x squared minus 1. And when we, is that visible? And yeah. So, x plus, so 1 over, you've just taken the reciprocal of both sides of the equation. Then if we rationalize the denominator by multiplying both numerator and denominator by x minus the square root of x squared minus 1, what we end up with is x minus the square root of x squared minus 1 over x squared minus x squared minus 1. Well, the x squareds cancel, and then we have a minus minus 1, which just all comes out. So a minus minus 1 before I write, I'll let you look at it. So this just all, everything in the denominators comes out to positive 1, because a minus and a minus is a plus. And again, the question that you may have already been asking a little bit as we've gone along in this lecture, well, why did we do that? Well, the reason that we did that is because if we add these two equations together, I'm going to erase this stuff up here to give us room. If we add these two equations together, we get these two equations together, and we'll get 2x, because these two terms will cancel, and these two terms will compound with each other. So we have e to the t plus e to the minus t equals 2x. Of course, you can already guess what we might do. Divide both sides by 2, so that we have x equals e to the t plus e to the minus t over 2. And note that, remember, given the hyperbola that we're on, the square root of x squared minus 1 is y. And so if instead of adding we subtract this from this, we will similarly get e to the t minus e to the minus t equals 2 square root of x squared minus 1, which is 2y. And then we divide both sides by 2, and we just get that this equals y. And so in summary, what we have shown, to summarize everything, what we have shown is that if we have this unit hyperbola, we have the unit hyperbola given by x squared minus y squared equals 1. Try to draw it nice. Then we have this shaded region. And we assert that this, and then we solve for this shaded region, and then we call this shaded region t over 2, some quantity t. We name it t over 2, and then we derive, based on this, we derive x equals e to the t minus e to the t plus e to the minus t over 2, which is of course cosh t, right? This is cosh t, so x equals cosh t, and this can be our definition. This is how we arrive at this definition of cosh t in this particular case. And then y equals sinh t, of course. Now, this actually does correspond more naturally to circular angles than I fumblingly stated in lecture 8, because if you have the unit circle, sorry, I'll leave this like this is x squared minus y squared equals 1. On the unit circle, unit circle x squared plus y squared equals 1. You have, say that the points are given by x equals cos t, y equals sine t, or we could call them theta, would be a more familiar thing to do, cos theta, sine theta. Well, the area of a circular arc, the area of the so theta is the arc length of this arc, but the area of the circular wedge right here is not quite theta, but it's theta over 2. Now you might be wondering, could we go through, why couldn't we go through the same process with the circle to derive an expression for sine and cosine that looks very nice and involves e to the such and such in the same way that we did for cosh and sinh with all these area integrals? And the truth is, in fact, we can. But something a little bit surprising happens at the end. So, first of all, now we're going to actually want this area plus this little extra area, so we're going to want a straight triangle plus a curvilinear triangle. And so A, let's call this shaded region A, which is of course theta over 2. So A equals x times the square root of 1 minus x squared over 2 plus this time the integral from x to 1 of the square root of 1 minus u squared du. And so this goes through, from this we can go through several of the same steps. Of course, if you think about how the fundamental theorem of calculus is stated, what we can do is we can switch these bounds and subtract. Right? So if you think about the fundamental theorem of calculus, if the antiderivative is going to be f of b minus f of a, so then if we switch the order of integration and subtract, then we get minus f of a minus f of b, which is of course no different from f of b minus f of a. So we do that rearrangement, and from there, all the steps go pretty much exactly the same as before. It's completely analogous. All the steps look quite similar, except, so I'll just write ... So then we come out to a final answer, which is not exactly the same, but is quite similar through the exact same steps. One over the square root of 1 minus 1 minus u squared du. And of course, this is just another way of arriving at, by the fundamental theorem of calculus, this just tells us something that we already know, which is that we have a half on everything, but it's really just saying that the derivative of inverse cosine is negative 1 over the square root of 1 minus u squared, which we already knew. But what we can see now that we didn't know before, perhaps, is analogous to the next step that we took with the hyperbola, but now it's going to have a surprising twist. And that is antiderivative theta of x, which of course, I mean, I could just say theta of x equals cosine inverse equals arc cos of x, call it a day. But instead of doing that, I'm going to do something that looks a bit like what we did before, but with some tricky new twist. 1 over I times the natural log of x plus I times the square root of 1 minus x squared, where I equals the square root of -1. And this, you can check that this right here, take the derivative of this function, and it will in fact be this, and evaluate this function at 0, and you get 0. So this is in fact this theta of x is this function, which is arc cosine of x. So what this is now is another expression for arc cosine of x. And so now let's do the same sort of inversion process that we did with coshx to get the expression for cosine. So theta equals, well, this, so first let's multiply everything times I. So we just have a log I theta equals the natural log of x plus I square root of 1 minus x squared. And then e to both sides, so e to the I theta equals x plus I square root of 1 minus x squared. At this point, you would be perfectly justified in being suspicious of, can we just shove a square root of -1 into the exponent for, e to the I theta, and you would be right to, I guess, perhaps to be suspicious of this act, but you could, if you suspend your disbelief, we can arrive at the end at something that will elucidate matters perhaps a little bit. So similarly, we're going to have e to the negative I theta by the same sort of rationalizing the denominator type of argument. 1 over e to the I theta, which is e to the negative I theta, equals x minus I times the square root of 1 minus x squared. And so then x equals e to the I theta plus e to the minus I theta over 2 and y equals 1 over I, or sorry, I'll just put it all over, 2I. It equals e to the I theta minus e to the minus I theta all over 2I. So that's one way of seeing things. So this is cosine of theta, the x coordinate. This is sine of theta, the y coordinate. And so from here, what do we do from here? Well, or where am I getting at? It might be a more natural question. So if we add these two things together, if we multiply this one times I and add it to this one, we get is x. You can check this. X. Oh, actually, I'll write it up here. We get that. X plus I times y from these expressions, x plus I times y, so the I comes out of the denominator. These two things cancel. You get e to the I theta plus e to the I theta over 2, which is just e to the I theta. So, I mean, you could even see this as a definition of e to the I theta. It's cosine theta x plus I times sine theta. And from this, what perhaps makes this whole idea of e to the I theta more convincing is the fact that e to the I theta prime, take the derivative with respect to theta, and we're going to see derivative of cosine theta, so that's minus sine theta minus sine theta plus I cosine theta. Right, so derivative of sine theta is cosine theta, and I, the square root of -1, is just a constant, so it doesn't affect any of the differentiation. So this, of course, we can factor out I is the square root of -1, so the negative 1 right here is I times I, and so then we factor that all out, and we get that this is I times cosine theta plus I sine theta. This whole thing equals I times e to the I theta. So of course, the chain rule is at work here. So if we put any other constant, e to the a theta, e to the b theta, the derivative would be b e to the b theta, or a e to the a theta, and I works exactly the same way. So that might convince you about why this is a reasonable way of thinking about e to the I theta. But then another kind of cool thing about this expression right here is we can plot these, what is called a complex number. It's part real number. It's a real number plus an imaginary number. It's called a complex number. So what we can do is we can plot complex numbers in the xy plane with an I-axis and an R-axis, a real axis and an imaginary axis, and then e to the I theta, for these various thetas, e to the I theta is going to have real coordinate or x coordinate cosine theta, imaginary coordinate or y coordinate sine theta, and e to the I theta is just going to be a very succinct expression for the unit circle. And that's sort of, I guess, the culmination of this discussion, other than another thing that can be pointed out quickly, is that from the expressions that we derived before, you may have noticed that cosine theta equals cosh of I theta and sine theta equals I times sinh of I theta. And so you can think of this as some sort of strange strange conversion between the coordinates of a circle and the coordinates of a hyperbola, both parameterized in terms of this area in the way that was demonstrated in the pictures before, the area between the ray and the x-axis. So this gives some sort of strange conversion between them. There's actually a more appealing conversion between the circle and the hyperbola that goes from the map, which can be seen from the map. Cosh T secant theta and sinh T goes with tangent theta. And this map has a very interesting interpretation in terms of the geometry of three-dimensional space, and you could actually see this relationship of what's really happening with this transformation. You could see this relationship if you have a lamp. So take the lampshade on the top of your lamp. So say even better if you have a cylindrical lampshade. So take your cylindrical lampshade and put it near to the wall, and have the rest of your room dark, the lampshade near to your wall. Then the light is going to project the rim of that lampshade. The rim of that lampshade is going to be projected by the light of the lamp onto your wall, and that circle is going to be projected as a hyperbola on your wall, and that corresponds to this transformation. Now, of course, you need to be holding it. The lamp has to be at steady on the ground at a right angle. Now, if you turned the lamp around in different directions and tried different things, you would see strange different things happening to the projection on your wall. Like if you were holding the lamp like this, it would be a circle. Then if you bent it a little bit, it would be an ellipse, and then you tilted it further. If you tilted it at 45 degrees, it would be a parabola, and then as you move towards 90 degrees, it would be a hyperbola, and then if you moved it directly to 90 degrees, it would be a hyperbola with this transformation, this correspondence between the coordinates. And so that's a way of interpreting that. And then another interesting thing is the fact that the hyperbolic angle here, the hyperbolic angle t over 2 equals the natural log of secant theta plus tangent theta. Over 2, of course, still over 2. And the reason for this is the corresponding hyperbolic angle, and the reason for this is that because it's a good thing this is the last lecture. This is my only marker left, and it's going bad. The reason for this is because e to the t equals cosh t plus sinh t. So if you want to extract out t, you take the natural log of cosh t plus sinh t. So the natural log of cosh t plus sinh t equals the natural log of e to the t equals t. So, yeah. And the reason I say it's interesting is that this quantity is a quantity. This quantity right here is a quantity that comes seemingly out of nowhere in our integration rules. This natural log of secant plus tangent is this quantity that comes seemingly out of nowhere in our integration rules. And now we have a nice geometric interpretation for it, which is pretty cool. It's pretty cool. It's interesting. Yeah, it's interesting. And something similar happens for the hyperbolic secant and the hyperbolic tangent. And it involves really arctangent, but that's, I guess, can be another story for another day. I've already poured massive amounts of interesting facts about circles and hyperbolas on you, and I hope that you have enjoyed this class and this lecture. If you have enjoyed this class, you probably enjoyed this lecture. No, if you enjoyed this lecture, you probably enjoyed this class. If you enjoyed this class, you still may not have enjoyed this lecture, but if you watched this far, then hopefully you probably did. So, have a good remainder of your summer. I guess there's not that long left, but it's been a pleasure having you in my first ever class that I've taught, let alone my first internet class, and I hope it has been somewhat enjoyable, and that my high hopes for the way that this class would transform the way you think about math, or give you a more hopeful view of it than you might get in other classes. I hope that it has worked to some extent, and that all my high hopes have not been lost on the learning experience of teaching. And so thank you for spending this 5 weeks with me in this interesting new experience for all of us.